Exercise 5b, the natural exponent. Today we're learning about the natural number e and its graph, and what you need to be able to do is remember the value of the number e and apply concepts of exponential functions to the base of the number e. So we keep talking about it. This is something called Euler's number. So E is approximately 2.71828. You don't really need to remember all of that, but it's kind of like pi. Pi is, everyone knows, it's 3.14, and it's very crucial in things like geometry and in circular functions. E, the natural number, is also something that pops up very often in exponentials and logarithms, and this particular topic. So Euler's number, the natural number, appears in many equations in maths and physics, things like light waves, sound waves, quantum waves, and we're going to be learning all about it today. But basically, I just want you to know that it's a number that's somewhere between 2 and 3, closer to 3. So in terms of the graph of e, so we're going to start graphing the natural exponent, which is e to the power of x. It's going to lie somewhere between 2 to the x and 10 to the x. So you can see 2 to the x goes up this slowly, 10 to the x is a lot steeper, and obviously e is just going to be slightly bigger than that too, so it's slightly more steeper than that. All the rest of the information about the graph of the exponential looks the same. So you're not going to really be able to tell the difference when you draw it. It's just more so remembering that the base that we're using is approximately 2.71 or 72 really, if you want to round it. Okay, so just starting off with some basics, state the transformations from the graph of e to the power of x to the following graphs. Because these are all really straightforward, we don't have to do the dash method. So we're just going to remember that we use DRT, thinking about our dilations, reflections, and translations. So starting with part A, I can see that we've got two dilations. I'll use a smaller highlight. There's the 3 and the 2. So we've got a dilation of factor 3 from the x-axis. So remember, on the outside, it's from the x-axis. And then on the inside, not only is it from the y-axis, but it's also the reciprocal. So it's the other way around. Okay, I can then see I've got a reflection on the outside. So reflection on the outside is again in the x-axis, affects the y values. And then finally, we've got a translation. Okay, so hopefully should be nice and easy. I'm not sure if I left myself enough space for part B. Let's make this a bit smaller and move that around. All right, part B, again, DRT, dilations, reflections, translations. All right, so there's no dilations. There is a reflection here, and then we have two translations. Now, I want you to remember that whenever you consider translations, it's always really important that anything that's in front of the x has been taken out in order to see the true translation. So what's actually happened here is that we've moved to the right, because when you take that negative out, you can see that it's x minus 1, and we do the opposite. All right, so first we're going to talk about the reflection. So that's going to be a reflection in the y-axis because it's attached to the x. And then we've got a translation of 1 unit to the right and 1 unit down. Okay, that's important, of course, to know all of these, because in a sec we're going to start sketching. So you're going to have to know what all of these different transformations are. Okay, this one says state the transformation required from this graph to this graph. Now, because we're going backwards, I personally prefer to do the dash method because it's not as obvious as just looking at it. We're going backwards. I suppose you can think of it as like what's happened to get to that transform graph and then do the opposite. But personally, I just don't want to make a mistake. I prefer to just do the dash method. So our old graph is this, and our new graph is this. So remembering our first step to isolate. Second step is to equate. Just be a dash there. And then the third step was to get, sorry, that was a bit crazy. I don't know why I wrote to the power of 3. That's just y dash. Our third step is to get y dash and x dash not by itself, which it's already done. And then our fourth step is to describe what has happened to old x and y, old y. So we can see again in order. So if you want to do DRT, you just need to separate this fraction here, which I might do just for the sake of keeping the order. All right, so we'll have a dilation, and then we've got a translation. So we'll dilate by factor 1/2 from, because it's the y values that we're affecting, so from the x-axis. And then we've got a translation 3 on 2 units up and 1 unit to the left. All right, so now that we understand how to transform, we're going to go ahead and do some sketching. It's going to be very similar to everything that we've already done. It's just now that we're using a base of e, which is just a normal exponential. So sketch each of the following over the implied domain and then state the range. So once again, we're going to figure out what transformations happen. We do have dilations, but dilations don't really matter in terms of what the graph is going to look like. So we're not going to really focus too much on those. What does matter a lot is our reflections and then of course our asymptote as well. So in terms of what's happened, we've got a reflection in the x and y axis. So normally our graph looks like this. If we were to reflect in both, we will end up with a graph that looks like that. And I might sometimes just draw a little just drawing just so I know which direction we're going in. And because we've moved 3 upwards, that implies that our asymptote is going to be at y is equal to 3. Okay, so let's go ahead and draw. We'll see in a sec if we need to find intercepts first. There's definitely no harm in finding your intercepts first. So if we've got y equals 3, yeah, so we should find our intercepts because we don't really know if our graph does this or that or that. So let's go ahead and find our intercepts and then we can put it in accurately. All right, for our y-intercept, we'll make x equal to 0. So that will just all be to the power of 0. E to the power of 0 is just 1, and then 3 minus 3 is 0. So that's actually really lovely because that means that it should just go straight through the origin. If you want to confirm, you can make y equal to 0 and rearrange and check that that is correct. But if our y is going through 0, then so should our x. I'm just going to check that one more time. E to the power of 0 is 1, and 3 times 1 is 3. 3 minus 3 is 0. Yeah, that looks like it's correct. All right, it's not very often that something works out that nicely. What a beautiful looking graph there. All right, wonderful. So that's sketching it over the implied domain, which would be R. And then for the range, well, our lowest value is negative infinity, our highest value is 3, and not including. All right, we'll try part B. Very similar idea in terms of our transformations. So we do have a dilation on the outside. Again, not going to really do much um, in terms of what the graph is going to look like. So we've got one dilation there. That's kind of it. We then do have a reflection, just one reflection. So this is going to be a reflection in the y-axis. So our graph is going to look something like that. And then we do have 2 translations. Now remember with your translations, if there is a number in front of the x, you need to take that out. So that's going to be x minus 3. So we've actually moved to the right by 3. And then we've moved up by 5. Now the up by 5 is the one that's actually important because that tells us our asymptote is equal to 5. Okay, the rest should be pretty straightforward. We can go ahead and sketch our graph now. So we're going to do an asymptote at 5. It's actually quite high given that the graph is going to look something like this. Sorry, from 10 like that. Awesome. No x-intercepts I can clearly see, so I just need to find my y-intercept. So to do that, I'm just going to make x equal to 0. Oops. That will be half e to the power of 3 plus, if I've expanded it, 5 over 2. 0, half e to the 3 plus 5 over 2. Not sure what's happened there. All right, fantastic. I'll just check that that's the last example, and it is for this exercise. All right, enjoy.